So we now can talk about the third fundamental circuit element, the inductor. If I had to define the inductor, I would say it's Faraday's law in a circuit. Okay, let's go back to our simplest circuit. We had a battery, we had highly conductive wires, and then we had a resistor, and then more highly conductive wires like that. Okay? The battery creates some potential, causes things to flow. It creates an EMF, E bat. Okay? So one side is high potential, one side is low potential. The current flows from the high to the low, and it flows through the resistor, R, and we got a delta V, a potential drop across the resistor that is equal, actually, to E bat. Depends on how you define the potential across the resistor. You can write it with a negative sign if it's a drop, or you can define it as positive as a drop, either way. But the point is, the potential you create here gets dropped across the resistor. The wires are so highly conductive that you get essentially no drop across the wires. That was the idea. And then you get a current. Current equals delta V over R, the resistance. That was fine. That's all that happened. Now let's imagine that's happening. Current's flowing. Everything's moving along. And while the current is flowing, we take the wire and we wrap it up into a solenoid. Like that. Well, if you do that, what's it going to do? Current's going to flow through a solenoid. It's going to create a B field right there. Okay? So, a solenoid creates B in the circuit. And then you could ask, what does that do to the current and the voltage and the blah and all this? And as I've drawn it here, it does nothing. Okay? Why would it do anything? Really, there's no voltage drop across those wires. They're perfectly conducting. But it had to make a B field. So it should take some energy to make the B field. Let's modify this slightly. E battery comes up here. Let's put in a switch to the resistor and then to this solenoid, which of course is the inductor that we're working towards. Okay? And let's throw the switch. All right? So if we throw the switch at time equals 0, we can plot the current. And just accept that it takes time for the current to get going. It's not instantaneous. Or you can imagine it's instantaneous. It doesn't really matter. The point is the current goes from here at 0 up to some value. Up to, actually it goes up to delta V E bat over R. Eventually all that potential drop is across the resistor. So there's the current you get to eventually. But it had to get there. It had to go from 0 to some current. It had to get going. So now let's plot the B field inside this is versus time. Let's plot the B field inside that little coil of wire we made in the circuit. All right. Well, the B field takes some time. While the current is building up, the B field has to build up to some constant value. Because the B field inside that coil is directly proportional to current. The more current you have, the more B you have. So here, now something is happening. Here we have a changing B field. Aha. What happens when you have a changing B field? It creates an electric field, right? Induction, magnetic induction, electromagnetic induction. So it creates it in here. And you'd say, can this coil cause induction to itself? And the answer is yes. Right? Electromagnetic fields don't care if there's a coil there or not. If we have a situation where there is a changing B field, it's going to create an electric field that wants to drive current the other way. What it effectively does is when the current grows and when the B field changes, you create an electric field that pushes back. It pushes against the growth of the current. In this case, it's actually the reason it takes the current some time to build up, is because it's actually fighting the E field there. What really happens is your battery potential that you create doesn't all drop across the resistor right away. A lot of it drops across here. So this is how inductors get involved in circuits is they have potential drops across them when the current is changing. Once the current is steady, there's no potential drop. It's just when current is changing. So let's see how we work that into circuit analysis. Let's look at it again. We had the battery. There's always some resistance. And then we have our inductor here. Right? So what's going to happen is the circuit, let's put in a switch so that we can imagine when it all started. The circuit creates an EL. That's the potential, or that's the EMF induced into this thing that we're going to call the inductor, induced in the inductor. It's called a back EMF. When something creates a potential back against the potential that started the current to flow in the first place, that's a back EMF that opposes EBAT. Right? So the battery EMF is over here. The battery EMF is what forces the current to flow, but then of course, according to Lenz's law, this thing pushes against the flow when you make a magnetic field, so this gets a potential going the other way. All right? So now the question is, how do we describe it? What equations do we use? How do we describe this EMF of the inductor? Well, it's equal minus d phi b dt. That's from Faraday's law of induction. But we don't want to really describe a current or a circuit in terms of phi, right? So we say, but actually the area is constant. All right? So instead of trying to write an equation for what EL equals exactly, we could say, let's write a proportionality. So we could say the EMF through the inductor is proportional to dB dt. Right? So now we're just saying proportional. I can ditch the minus sign, and phi is b times a is constant, so it's really proportional to dB dt. So we could describe circuits that way. But nobody wants to keep up with a magnetic field inside their circuit. Right? That's not something we think of when we do a circuit. But the geometry is constant. So since we have just this wound coil, we know that the B field magnitude is going to be proportional to the current. So if we know the B field is proportional to the current, then here's what we want to do, is we want to notice then that the EMF induced in this little thing is proportional to di dt. Okay? When we apply Faraday's law to a circuit, we throw out all the details. We just say, no, this EMF is proportional to di dt, and di dt is something we care about, right? That's the change in the current. Now we're talking about something that you analyze when you think about currents. The hard part is knowing what is the constant of proportionality between the two. You got to do all these calculations and think about the field, the magnetic field inside and the fringing fields, and is it an ideal solenoid or is it not ideal? How many turns does it have? Blah, blah, blah. So you don't deal with that. When you're doing circuits, you just say, here it is. EL is defined as minus, we'll put the minus sign back in because it's always minus L di dt. L is simply the constant of proportionality. It's the inductance of the little coil. So when you buy an inductor and put it in a circuit, they tell you what its inductance is. And there's two ways they could have figured out its inductance. They might have done a bunch of simulations of exactly what the field is doing and all the materials and all this stuff, or more likely, they just measure it. Right? So we don't actually know the exact field configuration around an inductor. We just know EL is proportional to the di dt, and that's the constant of proportionality. We rarely actually calculate the inductance for some inductor. It would be too complicated. We just know that we will get an inductance if we wrap the wire, usually around some certain material in the core. Here, let's look at the ideal solenoid. A geometry for which we can calculate the inductance. As I said, for typical devices you would buy, it's going to be very complicated. You would just measure it. But there is actually one we can calculate it for, and we should do that because then maybe we'll understand it a little better. So we have our circuit here, and this inductor is an ideal solenoid of length L, little l, this big L is now taken, and within turns, not turns per unit length, in turns. Now it's a little bit silly to call it an ideal solenoid when it's not infinitely long, right? If it's infinitely long, the turns are infinitely dense and you get a perfect field inside. What we're saying though is that it's wound very well. And even though it's a finite length, we're going to assume the field is perfectly uniform on the inside. So all that stuff we talked about in the last learning sequence is true. Okay, so let's then see if we can figure out how to calculate the inductance of this thing. So we need our equation for the back EMF created in the solenoid. So we have our definition. It means it's minus L di dt. But since this is a well-defined geometry, we also can do it from Faraday's law, where it's minus n, total number of turns, d phi b dt. Both of those are true. This one's treating it as just an unknown circuit element. This one is treating it with Faraday's law of induction. So the quickie thing then we can do is go ahead and stick these things in the time derivative. We know that they're constant. Let's just stick them in. And we can also just make them both positive to make it pretty. What we'll find is that d of Li dt equals d of n phi b dt. Well, in that case, the thing and the parentheses are equal, right? The time derivative of each of these is equal. We'll say the two things are also equal. So the inductance times I equals n times phi b. Okay? And we're trying to solve for the inductance L. L equals big N phi b over I. And now we can think back to what we calculated for the ideal solenoid. What was its magnetic field? It was mu naught big N I, that was B, and then times the flux would be the area A. Right, so there's N B times A, and that's over I. Okay. And if we put all that together, then what's going to happen? Let's see. So the I's go away. That's good. The inductance shouldn't depend on the actual current. It should be a constant for the device. We have N squared here, mu naught and A. So the inductance then for this ideal solenoid is mu naught, the total number of turns squared, times the area. So there you go. If you want to make a really big inductor, wrap it around a big area and put in a lot of turns and make it an ideal solenoid. And of course, these trends apply even if it's not an ideal solenoid. You still want a lot of turns. That helps you the most, and you want to wrap it on a fairly large area. So that's the one geometry where we can really calculate the inductance. Other geometries, the fringing fields, make it much more complicated.